I'm going to show you how to derive the special right triangles. We'll start with the 30, 60, 90 degree triangle. You want to go ahead and start with an equilateral triangle, which means that all of the sides and all of the angles are going to be equal to one another. Now I went ahead and I set the side lengths equal to 2 just because it's going to give us the answer in a form that we're very much used to, but I should note that you could derive this triangle using any side length that you want and you'd still get the same answer. So what we do first is we go ahead and we look at that 60-degree angle at the very top, and we want to go ahead and split this triangle into two separate triangles. And what we do is we have to take into account that when we split this angle right here, the 60-degree angle, what we're doing is we're splitting this directly in half, vertically, and this angle now becomes 30 degrees, and this side length now becomes 1. And I've drawn that over here. So what we want to do is we want to go ahead and just draw everything from our previous triangle onto this new triangle. And as I've said, we have 30 degrees now on this side. This side length is equal to 1. This is still equal to 60 degrees. And this side length is still equal to 2. Now, we want to go ahead and solve for this side of the triangle, but we don't know what this length is just yet. But we can use the Pythagorean theorem to figure this out. And what we get is that 1 squared plus this unknown side's length squared is equal to our hypotenuse squared, which is just 2. When we go ahead and simplify this, we are going to subtract the 1 squared onto the left side of the equation, and what we get is 4 minus 1 is equal to our unknown side squared. Take the square root of both sides, and although you would technically get a positive and negative for this root, you don't have to consider the negative because negative lengths don't exist. So what we get is that the proportion of this side of the triangle that we split is going to be equal to radical 3. Now, what this means is that the side opposite of the 90 degrees, right here, will always be twice as large as the side opposite the 30-degree angle, which is right here. So if we had a triangle that was, say, that had this length equal to 10, then, and it was a 30, 60, 90 degree triangle in this form, we would know that this side opposite of it is going to have a length of 5, which would be half of the length of 10 of this triangle. And one last thing that I want to note, keep in mind that these are just relative proportions. They only make sense in the context of real-world triangles, but when we get angles that are equal to 30, 60, and 90 degrees, or at least close enough, what we find is that these proportions hold true, that you would still get twice as big of an angle as you would for the hypotenuse as you would for this side length. Now we'll move on to the 45, 45, 90 degree triangle. So we want to start with just a regular square of length 1. And again, the lengths can be anything. I just arbitrarily chose 1 because it's going to give us the simplest answer. And what we want to do is we want to go ahead and bisect this square. We want to do this diagonally. And we'll go ahead and break this up into two different squares. And what we get is we'll copy the ones that we got for the side lengths from the first sides of the square. And now that we split this diagonally, we get half of the 90-degree angle on either side for 45 degrees and 45 degrees. We don't know what this side length is, but it shouldn't be too difficult to figure it out, considering we already did this for the previous problem. We'll use the Pythagorean theorem, and we get that 1 squared plus 1 squared is equal to our hypotenuse squared. We get 2 is equal to our hypotenuse squared, and then we'll take the square root, and what we're left with is that this hypotenuse is equal to radical 2. Now, what you want to notice here is that anytime that you have a triangle in which the opposite sides and the opposite angles, the opposite angles are going to be the same, then you know that these angles have to be the same. And similarly, if you have a triangle in which these sides that are opposite or adjacent to one another in this case, when the sides are equal to each other, you know these two angles have to be the same. These two angles have to be the same if these two side lengths are the same. And this is how you derive the special right triangles.